Yeah, so today I'd just like to give sort of an overview of work that we've been doing for the past couple of years, actually, that sort of I'll generically summarize as using GPUs and FPGAs as a service for HEP computing, although there's all sorts of little offshoots for this. And this is work that was done not just by me, but by this team that we have called the FastML team. You can look at the link there. It's sort of a real range of experiments and interests and things like that. So this is a really a large scope of work here. The basic reason for this work and the basic sort of reason that I think it's useful to talk about this is that, this is a plot from my experiment, CMS, the compact muon solenoid at CERN. But, I think a lot of experiments probably have similar plots that show that their computing needs are going to greatly outpace CPU growth if we keep sort of doing what we're doing. And this is only going to get worse as people's interests in machine learning and long high latency algorithms, complex algorithms increases. And what we believe is that coprocessors, and by that I in this talk will basically exclusively mean GPUs and FPGAs, although there are certainly other coprocessors that we could talk about, but the results that I'll show in here and the work that we've done focuses on these two. The coprocessors offer a very viable solution to this problem, particularly when you're dealing with algorithms that run either at very large batch or algorithms that are very computationally complex and require a lot of operations. So if you're going to use a coprocessor, the sort of simplest thing you could think about doing is to basically just attach the coprocessor to the CPU that you're currently running, whatever the workflow that you run is. And this is what's usually called direct connect. And so here the CPU is connected to the coprocessor with a PCI Express usually, and they just pass the inputs and outputs between each other. This is nice for testing things sometimes, but scaling this up becomes kind of difficult. You could say, what if I have different hardware types? Maybe I have a GPU and an FPGA. Now the CPU has to know what kind of coprocessor it's connected to. If the coprocessor is thinking about running multiple different algorithms, or if I have a very large number of CPUs, do I need to buy a coprocessor for every single CPU? So the main issue here is that the CPU, or the user that is, has to have some knowledge of the coprocessor in order to use this sort of design setup. And what we think is a slightly more sort of a generic way to design this is something called on-demand computing or as-a-service computing. The basic idea here is that as a user, I just want to run my workflow, and I don't really care how it actually gets to the coprocessor. As long as my stuff runs and it runs quickly, then I'm happy. And so the idea of as a service or on-demand computing is to basically connect to basically insert this intermediate server in this orange box here on the right. And so now instead of the user directly passing data to the coprocessor via the PCI Express, the user passes data over the network to the server, which is usually just another CPU, and then that server is in charge of managing data transfers to and from the coprocessor. And this is a way to really sort of make this a bit more generic, and you can see that this starts to become something that's a bit easier to scale. And it turns out that there's already existing tools from industry and from cloud computing where you could imagine this is also a really sort of almost necessary way to design the system. Just to maybe draw this in a slightly different way to make it a little easier to see, if these dark blue CPUs are the machines that you're running, whatever the workflow, the computing workflow that you're interested in accelerating, if these are the CPUs they run on, the as-a-service model says, okay, these grayed out CPUs are the servers, and these are connected. And so I can have as many connections as I want. There's an arbitrary number of connections that I can make between a given CPU that runs the workflow, a given client that is, and a given server. So I can have, all sorts of design setups. And I'll talk a little bit about how you might design, or the options for designing systems like this later on in the talk. But the basic idea is that these connections are kind of free. You can expand and contract them as you wish. And that if you have a direct connect set up here, you're sort of constrained to this completely linear one-to-one mapping, at least unless you're willing to start, adding in flags for if the machine has or does not, and the workflow can get a little messy. So this is the basic idea of as a service. As I mentioned, there's a lot of industry tools that are focused on this, and there's a lot of them that are focused on machine learning inference. And the basic reason for that is that machine learning inference has a very small number of inputs relative to the large number of operations. So, you have these very complex or potentially very complex deep learning algorithms, and you don't have to send a huge amount of data to the server in order to actually get the algorithm to run, because the large number of operations are running on a relatively small number of inputs. But the CPU, if the CPU were to try to run this algorithm, it would take a long time. So you get a very large speed up if you are doing this especially for complex machine learning inference. The other nice thing about doing this is that this is just true of as a service generically, that there's no knowledge of the hardware language required. So you don't have to know how to write in HLS or RTL for FPGAs. You don't have to know how to write in CUDA for GPUs, because the server basically manages all that, and so the user is completely abstracted. And this as a service setup is a growing computing of a lot of computing workflows for just this reason, that it's a very convenient way to set things up. So what I'd like to do now is to basically go through how we've done this setup for our purposes, and then go through some tests and some results that we've performed, and then sort of discuss what our sort of future work is, and how we think this might sort of fit in. So we have our sort of three main components of this as a service design shown here in the graphic. We have the client on the left in this green box. We have the server in this orange cloud, although it doesn't necessarily need to be in the cloud. And then that server is connected to the coprocessor here in the blue box on the right. So the coprocessor is the one that actually runs the inference. And to do this fast inference, we focus on the gRPC protocol. So the gRPC is a remote procedural call that was designed by Google. Basically allows you to write message protocols, message formats, and pass them. And there's relatively little overhead, so it's nice and fast. And the way we set this up is that the client is in charge of three things. It's responsible for formatting the inputs. It's responsible for sending the gRPC call to the server. Now, in our case, this is an asynchronous, non-blocking gRPC call, because that means that the client can run anything else in the workflow that it wants to run. It doesn't need the answer from the server. And this means that it can basically, it's not just sitting idle while it waits for a response back from the server. That's not to say that you can't do as a service if you don't have an asynchronous, non-blocking sort of call, or if you don't have that ability. But it certainly makes it's certainly the most optimal way to set this up. And then finally, the client's in charge of interpreting whatever response the server sends. The server is in charge of a little bit more, but basically the server is in charge of actually setting up the model, setting up the inference, running the inference, and then sending the inference back to the client. And then along the way, it's also useful if the server can do things like monitoring the network, monitoring the device utilization, things like that, so that you can actually sort of understand how the server's performing, whether it's working as you'd want it to work. I won't go into how we actually design these servers, just in the interest of time. But what I will say is that we use the NVIDIA Triton inference server for GPUs, and we wrote our own gRPC inference server with the same sort of gRPC protocol header format, using a tool we wrote, HLS for ML, as well as some tools from Xilinx. So we use Xilinx FPGAs in this case. And if you're interested, we can talk about that, but I won't go through those in the talk here. And then to actually benchmark these tests that we're going to run, we have three machine learning models. So the first we call Facile, which does an energy regression for individual channels in our hadronic calorimeter. We have what's called Deep Callow, which does sort of slightly larger cluster regression, so multiple channels together, trying to group those and determine the energy of the particle. And then finally, we use ResNet, which at this point is sort of a benchmark large or a benchmark semi-large machine learning model that's responsible for doing, in our case, for top quark image classification, although generically it's just an image network. So Facile is a completely dense network. Deep Callow and ResNet are built mainly out of convolutional layers, with obviously some fully connected layers at the very end. In terms of size, and this is basically the reason that these are chosen, Facile is very small. So Facile is around 2,000 parameters, but it can be run at very large batch. So there's 16,000 HCal channels in our detector, so we can run all of those simultaneously. They don't have any sort of crosstalk between them, at least in this model. So that's sort of the smallest model you might consider trying to run. And then moving down the spectrum, Deep Callow is a bit bigger. It's a few million parameters. And then ResNet is much bigger at around 2 million parameters. So we have this sort of range of sizes for the networks that they mean that we can sort of test the full, we can get an idea of what the full phase space looks like. I won't go through all the numbers in depth. Suffice it to say, the gains with respect to CPU inference are very large, but they vary, kind of widely depending on which models you look at here. Ranging from, an 8x speed up for Facile, which is this very small network, which is kind of what you'd expect, to something like 750x for Deep Callow. And these, and I'll go through some of these numbers a little more in details. The other reason that it's, one thing to point out here as I go through the results is, again, why we've picked these is because we think these sit in sort of interesting regions of where we might gain. So this is sort of a, a sketch of the parameter space for algorithms in terms of batch size and network bandwidth on the left. So, how much data you have to transfer to actually run this thing, and algorithm complexity on the right. And obviously, if it's a really tiny network and it has a very small batch, then there's not really much reason to think that you'll get a big gain from the network, and that's this red box in the left. Whereas if it's a really complex network that you run at really high batch, then that's the kind of thing that you really do think you should be able to gain from. So we obviously didn't choose anything in the bottom left corner here, but we tried to choose things that range this space here. Okay, so the first result that I'll just show quickly is the results when we just have, we start a server in Google Cloud in this case, and the server has one GPU attached to it. We then basically start a varying number of simultaneous clients, so simultaneous processes, and these all run from Fermilab, which is our accelerator laboratory. The inference then is basically the only thing running in these workflows. So the clients are just spamming the server with inference requests, and so this obviously isn't a very realistic workflow for the clients, but it is a way to really test or stress test the server and see what the maximal throughput it might be capable of is. So the Facile results are on the left, the Deep Callow results are in the middle, and then the ResNet results on the right. And the basic things that you notice is that they all saturate at a different throughput, which is kind of expected. There's no reason to expect them to follow some trend there. What is interesting is that the larger models saturate with fewer clients. So you can see that Facile takes around 50 clients to reach sort of full performance. You see that Deep Callow takes only 20 or so, and ResNet is already pretty close to maximal, somewhere between 10 and 20. So, the range that we're talking about here, sort of the scale at which they saturate goes down as the complexity goes up. And you also see, in the case of Facile, we were able to do this for multiple different types of GPUs, and you see, performance difference of around 10% or so, depending on if you're using a V100 or a T4 GPU. So these are all sort of, somewhat expected results. The one interesting thing that I'd like to talk about that you can do with as a service that you can't really do in the same way with Direct Connect is this idea of dynamic batching. So with dynamic batching, the idea is that you allow the server to wait for requests to build up until it has a set of them with a large enough batch that the processing the event on the GPU or processing the data on the GPU becomes really beneficial. So this is really useful in the case when you have small batch algorithms, or can be really useful in that case. And the other nice thing is that if your event processing is restricted to one event at a time, so that you're capped at, say, a batch size of 10 because you only get 10 inputs per event, the dynamic batching, because the server is abstracted from the client, and because it doesn't need to follow that same thing, it can actually just expand this out to multi-event processing. And it's a really simple change to do this on a server. And the results are really striking. So this is deep Callow. The triangles are without any optimization. So this just runs it at 200 batch. The blue squares are when you turn on dynamic batching, and you can see that the throughput basically just skyrockets. So you get about a 60x gain in terms of throughput. So you go from running it at essentially 10 batch to running at 200 batch. And then all of a sudden, instead of taking 10 clients to saturate the GPU here, you take around 1,000 clients. So this is it's a huge gain that you get for almost for free when you decide to do this sort of thing. We also have results for an FPGA server for a range of models. I won't go through them in too much depth, other than to say the facile model on the FPGA is very fast. And so the GPU gets up to 500 events per second. The facile, or the FPGA, can get up above 5,000 events per second. And the limitation here is actually not from the FPGA, it's from the CPU, we believe. For ResNet, you get sort of similar numbers between FPGA and GPU. The results there that I've showed are all with a workflow that just spams the server with requests. So they're not really a realistic workflow. So in an attempt to actually look at how as a service performs when you actually run a realistic workflow, we implemented the high-level trigger for CMS in this setup, and we basically took the algorithm that normally runs the hadronic calorimeter energy reconstruction, and we replaced it with our facile network. And then we accelerated that. So we did this in the cloud fully. So all the clients and all the servers were in the cloud. We did this both with GPUs and FPGAs. And the basic sort of results that we found were that we were able to achieve a 10% reduction in the computing time when we operated the reconstruction as a service. And this is the maximum achievable reduction that we could basically ever achieve for this algorithm. Because the HLT is composed of all sorts of other things that this change doesn't have any effect on. And indeed, the server is capable of serving a large number of these clients all at once without any loss in performance for the workflows. Because the FPGA is faster, it can serve more clients at once, but they can both serve a large number of them together. The same design that we've implemented for these sort of LHC level or LHC type tests can also be expanded to other experiments. So, complex neutrino detectors and the CNNs for them are really great candidates for this, I think, because they're very large, they're very computationally complex. And in this context, we looked at the ProtoJune single phase detector, which is a 770-ton RTPC, and in particular a CNN for hit classification that they use, which is around 11 million parameters. And the actual full integration as a service of this algorithm into the reconstruction is underway, but we were able to run tests similar to those that were run for the HLT that I just showed with a 4 GPU server. And what we found was that we were able to achieve a sustained 31,000 inferences per second per GPU connected to this machine. So that's the plot that you see on the bottom left here. And we were able to achieve about an order of magnitude reduction in the processing time with respect to the CPU, just by switching to as a service. We sort of did a similar test that I showed in the high-level trigger tests that's shown here on the bottom right, where we found that a single server can serve almost 300 jobs. This depends precisely on the batch size that you run the algorithm at, but somewhere between 200 and 300 without any loss in performance. And this is, I mean, this is a really, really cool thing to see. As I mentioned, you know, the as a service paradigm is not very restrictive in terms of how you design your sort of processing and your setup here. So, you know, there's all sorts of options. You can have servers for each algorithm. So that's sort of the plot in the bottom left, where maybe each of these nodes sends data that's specific to each of these algorithms into these boxes, and then the servers run and they send the results back. You could think of potentially having servers capable of managing multiple algorithms. So that's sort of the plot on the bottom right here, where the server has an FPGA that's responsible for running facile, and a GPU that's running another algorithm, and a GPU that's running another algorithm. So, and the server basically runs all of those simultaneously and then sends results back. You can think about cases where you have the actual accelerators connected to the processing nodes. So this is like kind of a direct connect as a service hybrid, but where the nodes are capable of passing information between each other, such that there's basically, you know, like a core that's running the server on this node, and then the other cores are doing sort of standard workflow. So things like that. So you can do some mix and match kinds of things here, and the possibilities are really quite large for how you design these things. Okay, so that was a pretty quick introduction, but I hope I've sort of shown you that the as a service computing model has a lot of existing tools, and a lot of tools that we're sort of developing that we can use to actually address computing challenges and computing issues. And these are really cohesive with ML usage, and they're very simple for, you know, the end compute user. I linked a couple papers here that we've written or at least submitted to a conference upcoming, if you're interested in some more details on these results. And I think the main point that we'd like to stress here is that this work is fairly generic. I mean, obviously the tests we've run are specific, but the work itself, I think, is fairly generic, and is capable of enabling generically heterogeneous systems to speed up real-time processing.
Dylan, I see Derek Fox has a question for you.
Okay.
Yeah, thanks very much. I was just curious if you could address the you know, the new software that the project wrote and why that was needed, as opposed to the other elements which seemed were more or less in place, and you were just you know, putting the infrastructure together. Thanks.
Yeah. So for GPUs, the sort of current software on the market from industry is already there's already a lot of coverage there. So, you know, this Triton inference server that I pointed out in this slide here is already very capable of doing this exact thing of, you know, of having a server running, and you send it these gRPC requests and it gives you the inference results back. For various reasons, the FPGA software and firmware is not as mature as the GPU-based software, and so we found that there is no open source FPGA as a service server code. It doesn't exist, so we basically had to write it ourselves. You know, some of the I mean, I can say explicitly that the ResNet models that we accelerated were run with Xilinx AI suite, which we can use to actually, you know, design the firmware to accelerate a large model. But the actual server code we still had to write ourselves, just because it didn't exist yet.
And
Does that answer your question?
Yeah, thanks. That's great. But having written that code, is it now sort of available for general use in that sense?
Yes. Yeah. So it's
I
realized I should have linked it on the slides here. But yeah, the code that we wrote, we've made open source, so that in principle anybody can check it out. It's on Git. I can if there's a place to sort of post slides after this meeting, if people are interested, I can update the slides with a link before I do that.
Oh yeah, please do send your slides. Yeah, that'd be great.
Just to say, right, it's the same software framework for the neutrinos and for the high energy physics. Right? We just copied it from one to the other. So we've already translated across experiments.
Got it.
That's the end of the slides.
Okay.
So if
Yeah.
if there are other questions.
I do I do have a question, but I wondered if anyone else would like to ask one first. I think we have a couple of minutes before we should move over to Eliu, so if he has time. Patrick Brady has a question.
Yeah, thanks for a really nice presentation. It's fascinating work. In terms of the sort of server and then the various workers and so on that are doing things, how much data are you pushing back and forth? I'm curious whether it's small or big or.
Yeah, this is a really good question. It turns out that as a service means that you really have to think about this. So I can say that for the GPU servers, we ran an explicit test where we turned on a server with 24 GPUs connected to it, and then we just spammed it. And it turns out that we were able to get up to 60 gigabits per second in terms of the bandwidth. And this is basically, at this point, the 24 GPU servers technically capable of handling more than this throughput in terms of inference, but the network just won't allow it. And we were also, it turns out that this result here is also, for the FPGAs, is also limited by network capabilities in AWS. So this is a 25 gigabit per second limit in AWS that cuts this one off.
Interesting.
So I should say that the GPU really was just a test to see how large the bandwidth we could crank up was. In principle, I don't think, most models, there wouldn't really be a need to run a 24 GPU server. You could just as easily split that into 4 or 6 GPU servers and you'd be fine. With this, it turns out that because the FPGA is capable of processing so many events per second for this particular model, that it actually is a real concern that you might be network limited as opposed to hardware limited.
And roughly what's that, I guess, what's the hit factor out of curiosity? Is it 50% or is it a factor of 10 or? So
for this network, for Facile, the actual inference kernel is capable of doing something like 10,000 events per second. So it's capable of doing what would correspond to roughly 100 gigabits per second. So, if you had full control over the network, I mean, if this was all local, 100 gigabit NIC would probably be enough to do it, but it would be close.
Got it. Lovely. Thank you.
Yeah, I just have one question, Dylan. So the way you expressed it, your CPU doesn't have to know about the coprocessor because the server knows that. What does the configuration that the server has for the coprocessors to which it's attached, what does that look like, or how hard is it to put together?
So it's a good question. It turns out that the configuration on the client side is actually very simple. The client is basically sends the data to an IP address, and the IP address is the server, and the server processes it. So in our case, we have things like a timeout limit to keep the request open for, and we send along a couple other pieces of information, basically, that are identifying about the size of the data and things like that. But at its core, it's really just an IP. So in principle, you can run the same config. You can take it from running on a GPU by pointing at one IP, and you can just change that single IP in the config and have it run on an FPGA server. And there's no extra changes that have to happen.
Okay, and you have to create the server has to know about the coprocessors, and you have to somehow encode that information on the server. Is that part difficult to do?
So that's that is the sort of more time intensive part, is because that is where you actually, I mean, you want to make sure that you've optimized that setup. But the point here is just that you do that basically once,
right,
and you don't have to do it again. And so that's what we've tried to do here. And certainly the NVIDIA, the Triton inference server is very good at this, is very good at allowing you to take a generic model and accelerate it.
Oh, okay, I get you. Okay, that was really interesting. Thanks very much for that.
Yeah, thanks for the chance here to present this stuff.
I can think of lots of applications for this. So thank Dylan, and then Eliu, if you can share your screen, and as before, I will watch for hands raised during Eliu's talk. Thanks again, Dylan.
Can you see the screen, Adam?
I can, yes, thank you.
Okay. So this initial slide is just to convey the message that in this project, we are bringing together experts from different disciplines. Dylan just talked about high energy physics. And we also have colleagues from the University of Washington and Mark Neubauer, who's in UIUC. For gravitational wave astrophysics, the knowledge of these challenges that we are facing comes from Eric and I. And we have also computer science experts and those that have been doing innovative computing for some time, including Song Han, Rankin, and Jane Jiao. And just to give you the overall vision of what we want to accomplish with this project. Gravitational wave astrophysics and high energy physics are quite disparate in terms of their challenges. Dylan just mentioned that they need to deal with very large volumes of data, and it is low latency. In gravitational wave astrophysics, on the other hand, when LIGO is broadcasting data, it is a lightweight data set, but it is high dimensional. So these are disparate challenges. And so with the ultimate goal of doing real-time inference, what we're trying to do is to design innovative algorithms to address these challenges. And then understand from the problems that we have across these fields to try to cross-pollinate the insights that we have been accumulating over time. And then once we have some solutions for these problems, then what we want to do is to produce commodity software that can be adapted by other colleagues in different disciplines so that they can also try to understand how to apply AI to solve their problems. And along the way, we are interested in training new AI practitioners and to make sure that this training enables them to apply their skills, not only in academia, but also in industry, and try to create a cycle in which this knowledge can be used, for example, for internships in industry, and then what they learn in these internships can be ported back into our projects. And this has been very successful. So to give you some examples of some work that we have been doing as part of this project, let me tell you about the problem of high dimensionality in gravitational wave astrophysics. So the goal of this project, that is titled High Dimensional Signal Manifolds, is to understand whether we can use deep learning to infer the individual spins of black hole mergers. And so we design an AI model where the architecture and the optimization schemes incorporate domain knowledge from general relativity. And so the parameter space is sufficiently deep that we need millions of waveforms to densely sample these signal manifolds. And so we experimented how long it would take to train a neural network to try to infer the individual spins of the black holes, and we realized that we needed about a month to train one of these neural networks. So this is not good. We don't have that much time. And so we decided to start using resources that we have at NCSA, like the Hardware Accelerated Learning Cluster. And so using all the 64 voltas that we have in that cluster, we were able to reduce the training to just 12 hours. Well, that's still not good enough when you're trying to explore a number of optimization schemes. So we ended up porting this framework in Summit at Oak Ridge. I assembled a team of experts both at NCSA and Oak Ridge and also from NVIDIA. And we were able to demonstrate strong scaling up to 6,000 voltas. As you can see in the bottom left panel, we addressed all the problems that come into optimization, like I/O, the data, how it is read, and then how it is distributed among different nodes. And apart from that, using over 1,000 GPUs, we were able to reduce the training stage to just 1 hour. And so the final product of this project, you can see this on the bottom right panel. The neural network processes signals, and then it provides an estimate for the astrophysical parameters of the source. Then we produce those putative signals and then computed the overlap or net product with the ground truth signal. And you can see that almost everything looks purple, which means that the model is performing really well. We want people to use this fully trained neural network, and people can go to the Data and Learning Hub for Science and download these, or use the containers that are provided at this resource and then run the model and verify these predictions. So, you know, the key point here is in gravitational wave astrophysics, the main challenge is the high dimensional parameter space, and we need to achieve convergence between AI and high performance computing to design these models. But once the model is fully trained, it can process data really fast, as you can go and verify that with the models we have in this Learning Hub for Science. Now, another application, it is related to gravitational wave denoising. And here the idea is a signal has been detected. Can we go and actually remove the noise and noise anomalies that are present in the data? And so we found that by using neural networks, we can, for example, take any of these detected gravitational waves that you see on the bottom right, feed this neural network with real LIGO data that contains a signal, and then the output is this clean signal that you can see there in the top row of these waveforms. Now, this is without incorporating the knowledge of the sensitivity of the detector. Once you whiten the signal, bringing into or taking into account how sensitive the detector is, you can see that they are performing really well. Now, if you look at that event that is labeled GW170608, what you see there is that the reconstruction is obviously dependent on the data quality. When there is a lot of noise, well, the algorithm is going to perform as best as it can. So there we have a model that, again, is open source, and you can verify that you can feed LIGO strain data, and the output is this clean signal. And as you can see in the bottom row, the overlap between the output of the neural network and the templates that have been predicted by template matching algorithms overlap really well. Close to 1 means that the recovery is really good. Now, if you see the panels that are on the bottom left, here what we are doing is we train the neural network with signals that describe non-spinning black holes. And so what we want to do now is figure out what happens when you inject a signal in real LIGO noise that has different parameters. And in this case, we chose black holes that are spinning and precessing. And as you can see here, the algorithm is capable of denoising these signals fairly well. The overlaps go between 99% to 93%. And as you can see on the one that is labeled template 2, there we incorporated as much spin and precision as possible. And the recovery is still decent. Now, so in different words, what this means is that these algorithms can generalize to signals that you do not use for training, which is a good sign. That means that you are doing a good job when training the neural network. Now, along these same lines, this is another very interesting project that has to do with cleaning the data again. And so here the idea is that this is a neural network that is going to remove linear, nonlinear, and non-stationary noise. And what you do here is that you take data from auxiliary channels that are witnessing a noise source, and then you want to see the contribution of this noise in the LIGO strain channel. And the panels that you see here presents a comparison between filters that are used customarily by template matching algorithms like the Wiener filter and the convolutional neural net deep clean. And this is showing data from the second observing run that was collected by the Hanford detector. And you can see that the algorithm is performing really well. In some cases, it has been found that by cleaning the data with this algorithm, you can improve the range of detectability of the detector, allowing the observation of signals with an increase in signal to noise ratio of up to 25%. And as Dylan mentioned in his talk, Eric and his student Tree are working with colleagues at NVIDIA to deploy this as a server so that any other type of data that is similar to LIGO that is streamed can also be cleaned with this algorithm. All right, so that was related to the processing of LIGO data, how you can use neural networks to characterize the signal manifolds, to clean signals from noise. But gravitational wave astrophysics goes beyond detecting and then characterizing gravitational waves. We also need to understand the properties of these sources. And so what we have also been doing is to understand whether deep learning can be used to learn the properties of complex physics phenomena like turbulence, which is very common, for example, in the modeling of neutron star mergers. And so what we have been doing is to produce these complex simulations using the Theta supercomputer in Argonne National Lab. And we have been able to demonstrate that we can use half of the system to produce these simulations. And then we use these data as training data to teach neural nets what the physics of turbulence is. And then once these neural nets are trained, what we do is we go and replace in the software stacks that are used to produce these simulations, the components that are compute intensive, those that demand sub-grid scale precision. And what we have found is that we can accelerate the software stack significantly, and we can produce high fidelity simulations without using high resolution. And you can see some snapshots of this work in the panels here. And this attracted attention of the community, and people wrote some blogs about this. So in the next couple of months, we hope that the code that we are developing to accelerate these waveforms is released, at least for two-dimensional compressible magnetohydrodynamics. And the ultimate goal of this type of analysis is that gradually we want to go to the level of actually replacing these components in software stacks that are used for binary neutron stars. Okay, so another interesting application, and this is along the lines of developing a server of what Dylan mentioned. Electromagnetic surveys are collecting an unprecedented amount of data that is also critical for some of the efforts that we do in gravitational wave astrophysics. And we have heard about the success using galaxy catalogs and gravitational waves to measure the Hubble constant, something that people call gravitational wave cosmology. Well, at the heart of doing this, we first need a complete galaxy catalog. And you know that, for example, the Dark Energy Survey has about 300 million galaxies. And well, someone needs to go and try to label them, right? And so an idea that we proposed is that we can try to leverage what we have learned from citizen science, deep learning, high performance computing, and scientific visualization to do this in an automated fashion. So Galaxy Zoo has been a great success, but that may not be scalable enough for DES and in the future for LSST. So again, we produce a neural network that can classify these galaxies automatically. And along the way, we also produce a visualization that shows how neural network is abstracting knowledge as it is processing data, and what sectors of the neural net are involved in the prediction when it is time to label these images. This again was picked up by Exceed and recently by the CEO of NVIDIA, who highlighted this work in his keynote. And again, this model, the fully trained neural network to do galaxy classification, is available at the Data and Learning Hub for Science. And I just want to finish with another application in astronomy. The idea is fairly similar. Now we are not looking at galaxies, but we are looking at star cluster images that are observed by the Hubble Space Telescope. So here the problem is a bit more challenging than classifying galaxies. If you look at the images that you see in the panels at the bottom of this slide, now each of these star clusters is observed in 5 different bands. And here there is a lot of noise. So for many years, the labeling of these images has been done by humans. The person who actually started this decades ago is Brad Whitmore, who's a co-author of this paper. And so Brad and Janice Lee from Caltech approached me and asked me whether it was possible to use deep learning to automate the classification of these images. And so over the course of about 6 months, we developed neural nets that actually outperform the accuracy of humans to classify these images. Brad was very excited about this. So what we ended up doing was to, again, port this model in the Data and Learning Hub for Science. One of my students also deployed this on AWS, and we have been interacting with staff scientists at IPAC and STSCI so that they use this model that now is used by several projects at these centers processing Hubble data. So this has been quite exciting, understanding how we can apply the knowledge that we have for other fields, which is one of the goals that we had for this project. And going beyond science, we are also interested in spreading the knowledge of how people can apply AI to address the computational signal processing challenges that they have. So locally at Illinois, we have been doing that, offering tutorials to students that are eager to get these skills. And also by offering tutorials in international conferences like the AAS meeting. Last year, by looking at the image we have there from Alicia Lanz, we had no idea how the community would respond to a tutorial of this nature. And so we were modest in our requests for space, but actually the room was overloaded and they had to provide an overflow room for people who were following the workshop. So it has been a very good experience. We also offer weekly AI seminars. Anyone is invited to attend these, and here we bring experts from across academia and industry that have been applying AI for a number of different topics. And, you know, corresponding to the invitation that we received to be here and talk about what we are doing, we have a virtual event next month, and we have invited you to participate. Mario is going to be giving a presentation in this workshop. And the idea is that we want to explore ways in which we may work together for the creation of Harnessing the Data Revolution Institute. So I hope that some of you attend this conference and we figure out some mechanisms to work together for the creation of one of these institutes. And talking about this, you know, just to prepare or lay the groundwork for these conversations, the vision that we have, and this is something that is in change, in evolution, is that this is the basic pillars of what we are doing right now. We want to do real-time inference for big data physics experiments like LIGO and high energy physics. We have disparate challenges. In gravitational waves, we need to study a high dimensional parameter space, and we need the convergence of HPC and AI to develop these models. In high energy physics, as Dylan described, The challenges are slightly different. Here you have high volume of data, low latency data, and then you need to produce compact models that can process data very fast. And so, you know, the work that we have been doing has been very well received by the NSF, but we also know that just having these components is not enough to create an HDR institute. We need to go beyond this. And so ideas that we have to actually accomplish this are the following. If you look at the top left, we want to build upon what we have right now, and we want to incorporate collaborators that have similar challenges in terms of computing and signal processing. On the top right, well, the elements that we have right now that are working well are the convergence of AI and HPC for gravitational waves, and AI at the edge for high energy physics. We have been producing open source commodity scientific software so that the broader community can get access to it. And we are also exploring mechanisms in which this can be cross-pollinated with other disciplines. And now what we want to do for an institute is to strengthen these activities with experts that have been working at the interface and innovative computing. Beyond this, if you look at the bottom left, we want to increase the synergies that we have with government and industry, going beyond NVIDIA, IBM, and other companies with which we interact very closely. And then finally, another important component of this institute would be to broaden the educational programs that we have to increase data literacy, and also to make sure that when we are producing these AI solutions, we follow best practices in terms of scientific software. And so these are the minimal elements that we are considering for the creation of such an institute. And we look forward to conversations on how we could try to work together towards the creation of this institute. That's it for me, Adam, if anyone has questions.
Yes, thanks very much, Eliu. Time is running a bit short, but if anybody would like to raise their hand and ask a question, I have a question or two of my own, but I would put those until afterwards. Derek Fox has a question.
So what are your plans for this lower left square, broadening industry and government synergies? How do you plan to tackle that? Thanks. So it just happens that for the type of work that we do, we have contacts with different companies. So Phil has contacts with people that are producing, for example, FPGAs, another AI at the edge hardware. I, for example, work with people that are more at the interface of HPC and AI. And so the idea is to try to see how we can bring all of these together, and going beyond, there will be other domains that are interacting with other companies. So we want to understand that. Tools that are provided, for example, for innovative computing, like, for example, the Cerebras chips that are now available at NeoCortex at Pittsburgh Supercomputing Center, how this could be used, for example, for the big data problems that we have during training. So there are other opportunities here that we have not explored yet, and we want to go and try to incorporate these innovative ideas into an institute. Now, in terms of government, we also need to make sure that the software that we produce follows these new policies about, humane and ethical AI. So we also need to go and hear from these experts and incorporate these ideas in the activities that we will be leading. Okay, thanks.
So Eliu, I have many questions, but we have little time. So one question I would like to ask, we're thinking of moving ahead to an institute. If I'm a researcher and I'm pretty sure I would like to use a sort of advanced machine learning technique, and I understand my problem very well, but I don't know very much about AI, what would be my sort of roadmap trajectory in the institute era to get enough help to get you know, on the right sort of hardware and able to deploy the right sort of tools?
This is a great question, Adam. And this is the same question that we get from people in companies or in the healthcare sector. They know that they have some problems, but they don't see how AI could provide a solution. So what we do is we organize some events that we call them Bring Your Data challenges. And so they bring a domain expert, and we have their AI and software experts. And so they describe what the problem is, and then we understand the nature of the data, and then we figure out what would be the best hardware and the best AI solution for a given problem. And then we continue working with them. And this is an end-to-end process. This starts at how the data is prepared, and then how the data is going to be processed by neural networks that will incorporate the domain expertise of the person to extract the knowledge that we want from the data. So I would say that this is a multi-step process. First, we need to understand the challenge and the nature of the data that you have. And then this is where, having defined this, we start designing the neural networks. But this is not a problem where you want to just dump your problem on a computer science expert. This is something that should be addressed by, concurrently by the domain and the AI expert. And after that, then, it is plug and play. But it is necessary that computer scientists and domain experts work here on an equal footing. We cannot just go and let the AI expert go and figure out my problems. That doesn't work. We have experienced that with the nets that we design. They look beautiful. The architecture is very sophisticated. If they don't have any domain knowledge, they are useless.
Right. Yeah. I work very often in the sort of consulting business with domain scientists, and that matches my my understanding of the best way to leverage the scientific domain expertise and the CS expertise.